really be honored to be here to present on behalf of Rust for Linux team. And so let's just start with the basics, right? What is Rust for Linux? So this is a project that aims to bring Rust support into the Linux kernel. And this includes writing kernel modules, like drivers of file system in Rust, with little unsafe code as possible. So we aim to provide as much safe abstractions for the kernel API as possible. But the goal is not to rewrite the whole kernel, right? The kernel has 30 years of history and has a very large code base with more than 20 million lines of C code. And it's basically just infeasible to rewrite everything in Rust. So whenever you try to introduce Rust to a code base, you will always be asked the question, why Rust? Right? It's like the thing on this slide is not very different from what other projects does, like what the NTP project. Like we want to defend against undefined behaviors. Obviously, CVEs has been happening on the kernel every single year. There are always undiscovered secure vulnerabilities with 20 million lines of C code. And then it's good that Rust provides a clear boundary between safe and unsafe code. It has these nice features like rich type systems, some types pattern matching, and really simplify the error handling in driver code by quite a lot. We also can leverage the rich tool system that Rust has, Rust doc, Rust format, and Clippy, etc. So a very brief history of Rust for Linux. Right? The project started at late 2019, and the first RFC hits Linux kernel mailing list in 2021, I think around April-ish. And then last year, around just a year ago, a minimal pull request is finally merged into the mainline and in experimental status. So now the kernel has 2 languages support, C and Rust. So a brief update of the status of projects. So when the project begins, there's just 3 team members working on this project, Miguel, Alex, and Wesson. And on 2021, the team grows a bit with 3 more members. And this year, the team grew to 9 members just like a few months ago. And some of you know that we do kernel development quite differently from the Rust torching, for example. We use predominantly mailing list for code reviews, patch, we don't call pull requests, we call patch series. And then all the review and code review and approval happens on the mailing list. So we now have around 460 subscribers for the Rust for Linux mailing list. If you are keen on following the project update, I encourage you to follow the mailing list. And then we also run a public Zulip instance. Now with more than 500 users and 70-ish active users. And obviously we have more stuff on GitHub, but we don't actually use GitHub for development anymore, just because that's usually not a tool used for the Linux kernel. And you can see around a year ago when we are merged into a Linux kernel upstream, then you can see the slope difference, and more people are interested in the project. So these are the features that we have in the prototypical branch before being merged into the kernel. We actually had a lot of features implemented by that time with the module infrastructure, like a dozen of synchronization primitives. We have walk queue, platform device, character device, file system support, a little bit of power management, a very core functionality in networking, and we have actually asynchronous runtime implemented using walk queues. So before, in 2022, you actually can write async functions and doing networking stuff with our prototypical branch. However, in 2023, nowadays, we actually have less things in the kernel, in the Rust for Linux project, because the kernel has a policy which, if an API has no user, it cannot be upstreamed. So what we currently have is the really basic things. We have the basic module infrastructure. We have the very basic synchronization primitives, mutex, binlogs, and convars. And then in last year, we have a new ping infrastructure, which I will cover in more detail later, which is basically just ironed out in the past year. And then we have a new walk queue abstraction, but it's quite mature at the moment, but yet to be merged. So in the process of taking things out and remerging things, we actually take the opportunity to review how the API should look like, whether it's actually sound, and then evolve the API over time. So C upstream is quite different from the thing we used to have in the Rust branch really. And then we are basically waiting for users to actually use the API that we have. So we still, like, the code is not being taken away. There's just a large reservoir that we can basically waiting for users to actually use them so we can pick up and upstream them. So this is an overview of how things actually build in the kernel. We take libcall directly from raw source tree. But for alloc, we actually use a custom fork of alloc instead of using the upstream alloc. And then we have all stuff basically currently lives in a monolithic kernel crate. This is due to how kernel build system works. Its kbuild is a build system designed for C code, which does not have idea of dependencies, right? Because everything is in header files. You include everything, so you can build drivers before the subsystems themselves are built. And this is not the case for Rust code. You have to actually generate the metadata for the query you depend on before you can compile the drivers. So there's currently some work being going on to actually split kernel crate into multiple ones and then actually support the dependencies in the kernel build system. But for now, all the abstractions still live in monolithic kernel crate. And we also have a bunch of macros. And then we use bindgen to generate bindings from the C header files. There's one issue, which is static inline functions and macros, which are quite heavily used in the kernel. So we actually have to create some additional helpers to turn them into exportable C functions. And this is for the drivers, we're really trying to provide safe abstraction for all the drivers so that we currently actually already forbid drivers from calling into the C bindings directly. So they have to go through any subsystem abstraction provided by the kernel crate. If someone wants to use a binding that's not currently provided, they actually have to think of what abstraction should look like and then design or upstream the abstractions. So we currently have quite a few users or potential users that are looking into Rust for Linux. We have Android Binder, which they are trying to rewrite their C implementation in Rust. We have notably open source project, Asahi Linux project, have implemented their Apple Silicon graphics driver entirely in Rust. And I think recently they passed OpenGL certification, and I think they support more OpenGL features than Apple's own driver on macOS, which is quite a notable achievement. And we have Samsung looking at the block devices, and then there's two file system users, potential users. Microsoft is looking into using TAR-FS, and Cisco is looking into Puzzle-FS. And we'll also have Clever interested in implementing codec. Like, the Rust is really good for parsing stuff, right? So they're trying to see if they can implement codec in the video for Linux using Rust. So this is about the status update so far. And people might be thinking, like, the project has already been 3 years, and why do we have so little things in the kernel? And why are we moving kind of slowly than maybe other projects? Well, the answer is it's actually very difficult. So here are a bunch of Rust expressions. If you are experienced Rust users, you might be very familiar with, right? But they all have one thing in common, right? What's in common between all these expressions?
Allocation.
Yeah, they all have allocation. And actually, they all assume allocation will never fail, right? They all use infallible allocation. But allocation is something that might be, you can do allocations very easily, and sometimes implicitly in real space, Rust code, right? Some into implementations will do allocation for you. But allocation is not trivial in the kernel. Why? Because allocation can fail, allocation can sleep, and allocation has certain overhead. Right? If your computer is in low memory condition, then try to allocate, it may fail. Or in some cases, it involves taking some user space memory and put them into swap, or maybe trigger out-of-memory killer to actually kill some user space process to reclaim memory so the kernel can use it. So this means allocation is an operation that can block and can sleep. So it's not usable in all contexts. And the allocation really changes everything in Rust for Linux. So here on the left is some C code, which involves pushing something into the walk queue. Right? So we have a struct walk, which contains a walk struct. And then when you're trying to put it into a walk queue, what you do is you basically give a function pointer, and then you say queue walk to queue it into the walk queue. And then when the walk queue actually go and try to execute this walk item, you use container of to recover this and then operate on it. Right? If you're experienced in Rust coding, you're probably already thinking what would be the idiomatic or what would be the economic Rust API. Right? You may think, okay, it may just look like this, right? We have a system walk queue, and then we just call enqueue and give a closure, and every data needed to do the processing can be closure captures. But if you think about this, right, how are you actually going to implement the enqueue function? Well, actually, you have to do allocations. Either you have to create something and push it into a linked list, or you have to a vector and you stop push. But all of these involve allocation. If you have certain capacity of your vector and you try to push one additional element, you might have to reallocate. And also, the closure have indeterminate size, so you might have to box it to turn into FN1. So all of these can allocate. Okay, so you may think, okay, how about we just make it failable, right? And we can use the very economic Rust error handling in this case. Well, yes, it works in some cases, but not all of them. So one particular case of using walk queue is that if you're in a context where you couldn't sleep or couldn't do some operation, you can defer the operation to a later time to execute. For example, if you're trying to free some resources inside a very time-critical process, okay, I will queue the destruction process, destruction to a walk queue and then do it later, right? But if you say, okay, I need to allocate before I can free this, then it's trouble, right? If you're already in low memory condition, and if you try to queue the destruction of a resource, and if it fails to allocate, what are you going to do with it? Are you going to leak the resource? And then it will make the low memory condition even worse. And then in some contexts, you just don't have a way to allocate, right? For example, if you have interrupt coming and the allocation fails, are you just going to throw the interrupt signal at once? That's not something achievable. So this API is not doable in the kernel. So this is the API we have now, right? You can see it's very complex, right? It actually has more lines than the C code. But a good thing is that there's no single unsafe thing there, which is a good thing. We managed to hide all the complexity of unsafety inside our abstractions. But this is more complicated. You see, we have results. So when we're initializing the struct, it can fail. But when you queue, you can see when in the queuing part, there's no question mark here, so it can never fail. We use a custom arc. We have an intrusive data structure so that we can avoid additional allocations. We have some macros for pin initialization, more on this later. And then we use a macro magic to provide safe container off. And then we use a macro to do our own track caller, which is something that's unfortunately Rust track caller wouldn't be able to do. Right? So there's a lot on this slide, and the whole point, you don't have to understand this, right? The whole point is to show that Rust for Linux is very complex. The idea is, the design is very complicated because the kernel has certain need, which user space Rust does not have to deal with. And the complexity is really basically allocation. Allocation really changes everything in our API design. Why does this have animation? So I remove this. So we currently use a fork of alloc. And because we have to add more try methods than that's available upstream. For example, we couldn't, a vector, we couldn't use the push function. We have to use try push, which is not upstream. So we have to add this in our custom fork. And also we remove some stuff. Eventually, we probably have to diverge and define our own custom box and VAG, just because the API that's provided by the alloc crate probably not going to suit our need. So this is, you can see, we have a custom type not using the alloc arc. So why are we creating our own arc? I think this is the old slide, not the updated one. But anyway, so the arc provided by alloc crate is cool, right? But it has something that we have a different need. So for example, the arc provided by alloc has a weak references, which we don't use. And that means we are wasting 8 bytes for each allocation. And then it's not pinged by default, so it provides get mute and make mute, which is quite helpful for certain user space applications. But in the kernel, almost everything is pinged. And that means we have to, whenever we write an arc, we have to write ping arc everywhere, which is a pain. So our custom version of arc, we have everything pinged by default. So you can just use a from import to convert arc into ping arc. And the biggest issue with the alloc version of arc is that actually aborts on overflow. And the kernel reference count does not abort on overflow, but it saturates. And whenever overflow happens, it puts it into a saturation state, and then the reference count will never leave this saturation state. So it can cause some memory leak, but it will never abort, because if a kernel aborts, then you're not getting your system log anymore, and there's no way to know that abort happened for whatever reason. So the kernel really tries to avoid abort and panic in all situations possible. So in summary, kernel has a very different need for arc compared to user space, right? So we need a way to define our own smart pointers, and then ideally have them as featureful as the provided ones in the standard library. And this means we need the ability to use them as method receivers, the self types, and we need to use unsizing and the dynamic dispatch, essentially. So actually, like we have, currently upstream we have less than 10 feature gates, unstable feature gates that we need for the Rust for Linux. And half of them are related to smart pointers. So this is an area that we really want Rust language to provide support, so we can move towards a stable Rust as soon as possible. And another issue that we have is the kernel uses a lot of intrusive linked lists. So this is how a linked list looks like in the kernel, right? The list head itself is part of the linked list. This means that when the linked list is empty, it looks like this. So it points to itself. And what does this mean? It means that the intrusive data structures in the kernel are not only unmovable, but they are unmovable from the very beginning of initialization. So this means the ping is not sufficient for us, because you can't create something and then ping it into place. It has to be created into place to begin with. So like, you can define a mutex like this, right? If you have to use what's provided by Rust now, you have to have an unsafe new function, an unsafe initialization function, and you have to use two unsafes to actually create something. And that's not a good sign, right? Because everything in the kernel almost everything in the kernel is pinged. And having to use unsafe to just create something is very bad for economics. So what we do is that we have this new full pinning infrastructure for performing pin initialization in place. This is like the initial design came about 2 years ago, and then in the past year we really evolved it and make it economic and as similar to normal Rust code as possible. So we have two macros here. We have a ping data macro and we have ping init macro, and we had all the unsafety inside these. And you can see there's also a very special syntax, meaning that this have to be pinned in place. So this is nice stopgap for us so that we can actually use not unsafe to pin things into place. But the best unfortunate thing is that these are infections. So if a struct have to be pinned in place, then all the struct containing the struct also have to be pinned in place. So ideally, so basically all the structs creation requires these macros to be used. So ideally we want some language support, but we're also unsure what form it will look like. Yeah, so if you have any ideas of how this thing could be implemented as a language feature, please contact me. And also ensure that all the Rust team members in the loop. So we have a lot of macros, you probably already see, both declarative and procedural. And we're kind of in a dilemma here, right? Procedural macros are painful to write without using sing, and declarative macro are more limited in its expressiveness, or if you're not resorting to token munchers, which can do everything, but at that point, it's not maintainable anymore. So one question many people ask is, why not just use sing? Well, yeah, the kernel has its difficulties here. So first of all, we couldn't really download dependency from the internet. So people say, okay, why not vend it? Well, current upstream Rust port has just around 6,000 lines of code. And even the early prototypical branch have 15,000 lines of code, obviously without counting the drivers. So it will be a very big ask to the kernel community that can we actually pull 35,000 lines of dependencies into Rust for Linux? And most people don't like that. And it also means basically in the kernel tree, we'll have a parser of all the Rust language. So maybe the Rust language, like the standard library, the proc macro crate can give us a little bit more API than current provides. So this is just brainstorming essentially. Maybe we can have this pass block and pass expression methods that basically just give a token stream. It doesn't have to be AST, so you don't have to actually commit into a long-term stable API. So if we, in many cases, just having a token stream say, okay, this is a token stream represent type will be sufficient in many cases. These are deleted slides, which somehow is not updated here, which I will just skip through. Wait. And another issue where we're struggling with is that we have the floating point at 28-bit integers are causing us troubles. As you may know, many of these things are actually not built into like the instruction set. So you have to actually pull in compiler built-ins to support them. But the issue is that we actually don't want any kernel code to actually use floating points, right? Because like either you have to make sure the hardware instructions is there, and then you actually save all the user space state to actually back them up and ensure that you wouldn't actually which can be slow and also large dependencies. So we currently have all these stub functions inside of the built-in crate, and we are not pulling compiler built-ins as our dependency. And we actually have to be very careful because the kernel currently rely on these symbols not being present to prevent C code from using them. So we can have to some magic to actually tweak the object files generated by libc object files to redirect these stubs so that they can only be emitted by libc. And if any other compilation unit emits these symbols, they actually cause linker errors. And many people say, okay, if you don't really care, like you don't want these features, why couldn't you just use F function sections or LTO to compile them out, right? It could be a linker time optimization. Well, the answer is the kernel drivers can be compiled as modules, which are similar to dynamic loading. So if one of the symbol can possibly be used by one of the module, and note that we support all of tree modules, not just in-tree modules, then the symbols have to be present. So for Rust for Linux, this means that all of libc and liballoc have to be linked into the kernel image. We couldn't actually strip them away. And this means if we have a feature that we don't use, but it's present in libc, then it will be inside the kernel image, which can cause issues with binary size. And like accidental usage of these APIs is also possible. So what we want is maybe modularization of core and alloc. So currently, we already have an experimental feature gate called no-fp format parse, which strips a large chunk of binary size away from libc, because parsing and formatting are actually quite expensive, quite heavy operations on binary size. So we enable this flag when compiling libc for the kernel to remove them. But one idea is that could we actually have some target flags or call-gen flags to actually remove floating point support completely from language, so we can actually prevent accidental usage of these APIs. And another thing is 128-bit integers, although these are usually less of an issue compared to floating points. There's also some other features that have quite big impact on binary size that we probably wouldn't use, like Unicode. And we also use this flag to remove any possibly infallible allocation APIs from the allocrate. And some other things that we don't use is like RC, duration, IP in core. Like you may think, oh, why couldn't we use duration? Well, actually, duration is currently implemented as second plus sub-second nanoseconds. And in the kernel, actually, we just use a 64-bit integer. And then converting between these two formats can be quite costly because it involves division operation, which on some embedded systems, actually there's no hardware support for division. So actually call into library routines which are quite slow. Or maybe instead of removing things from core, there could be a stripped down part of core, which like, I don't know, that's the name, core. It just contains the items and intrinsics that couldn't be implemented outside the compiler. Right? Just like the way we use C in the kernel, we don't use a lot of compiler features. We basically just use the ready core part and re-implement many of these. Or maybe call it liblang or librust. I don't know. Yeah. So wrapping up, kernel is very different from user space. That's one lesson that we definitely learned. And then failover allocation really dramatically changed the way we actually think about Rust and think about API. And intrusive data structure is also some very large important points that we differ. And then I actually skipped this in the slide, synchronization primitives. But dynamic module loading is an area that we really want to see like feature realization or basically modularization of the standard library. And then we also, like in many cases, the issue can be solved by using proc macros. But ideally, we don't use proc macros for all the places because otherwise, we basically is using a dialect of Rust if we use proc macros in all the cases. So yeah, language support is definitely appreciated.
Thank you, Gary. 我们进入那个提问环节。在这之前，我先提一个问题，能回到那个自定义那个mutex 那个 mutex 那个代码。
Why there's so many animations? I delete all of them. Do we have another copy here? Okay, we don't have. I don't think we have another copy. Okay. Which slide? This one? Oh, this one or this one? Which one is that? Is this one?
我的问题就是，上面这个 U， 它是一个它是必须去调用这个下面的方法。既然下面这个方法它就是如果把下面的方法给它把这个文档移下来，就是让它把那个 safety 的文档移下来，就是在它调用的时候，在 new 调用的时候。就是让那个，就是相当于是给这个 unit 这个做一个安全的收效，然后那个 new 那个是不是可以去掉？
Well, the question was if could we move the safety document down and remove the unsafe from the new? The answer is we actually have to use two unsafes here because when creating a new mutex, you have to commit into initializing it. Right? You couldn't create a mutex without initializing it and then use it right away. So this had to be done this way. And then the init function also have to be unsafe because you can only initialize something once. If a mutex is currently in use, you can initialize it again. And this was the API that we had, but in the past year we have removed them. And so the new APIs, we currently only provide these kind of abstractions. So you now use a new mutex macro to actually initialize it, to create an initializer which allows you to initialize in place.
So when you're writing Rust for the kernel, there are all these special rules that you have to follow and things you can't do and so on. But that must be true for C code as well. There must be a lot of C code features that you can't use or special ways of doing things. So is it more unusual? It's like kernel Rust more different
Yes, because in kernel in C code there's no safe and unsafe boundaries. So like we could make the Rust code very similar to other Rust code if we have unsafe everywhere. We have this Rust code very similar to the kernel C code by having unsafe everywhere. But whenever we actually try to provide safe abstractions to things, we make things more complicated. Just because usually like who would imagine initialize things would require unsafe in C code.
So I actually have two questions. First of all, it's my understanding that in the kernel there are certain functions that can only be called in certain contexts, or
Yes.
or the opposite, that cannot be called in certain contexts, like intro context. Have you considered using some form of linting or custom attributes to be able to detect such cases?
Yes, that's one of my other work, which is we have a tool called K-lint, which basically adds custom colors to functions. So one thing we could detect using that tool is to check if sleeper function is called in a non-sleeper atomic context, or vice versa. But that tool is not currently in a it works for simple cases, but not for very complex drivers. So there's some effort try to improve this. But we definitely think it's like. So basically, like sleeping inside atomic context in the kernel is one thing that Rust safety guarantee couldn't actually cover for us, and we actually rely on it to element use for free. So like if you write complete safe code that passes Rust C, it's still not guaranteed to be UB free in the kernel. So we have to add these additional checks, which are custom.
Thank you. My second question was, you said that the development of Rust for Linux is mainly based on mailing lists
Yeah.
rather than GitHub, which is more the standard for the Rust community. Is this something that was imposed from up above, or something that you chose to do?
I don't really want. Well, okay. Let me answer a separate question. Right? So we have before we actually get merged in, upstream. Most of development work actually happens on GitHub. Right? So currently the canonical branch for Rust for Linux still on GitHub. It's github.com/rust4linux/linux, and there was a branch called Rust Next for development. Right? But when it's upstream, we have to follow the norm in the kernel community, which is using the mailing list for everything. We still welcome people to send pull requests to us. Like we can get some reviews before you actually want to send this to the mailing list. But if you really want to get it merged, it has to send it to the mailing list before collecting the review buys, and then get actually picked up.
我的问题是这样的，就是说内核积累了这么多年，它肯定有一些自己的基础设施 ，JC、RQ 啊，或者是多端上这种自己调的，它有自己的编程规范。Rust 自己的也有自己的编程规范。然后我们为了把用 Rust 写 OS 的，它其实有把相当于让 Rust 的用户按 OS 的方式来写 Rust， 写这个kernel module 或者MS 这种 module。就说这种的话，就是说会不会让 Rust 的人会觉得很别扭？另外一个点就是说，你能看到说语言能对它改变以后，语言现在长成这样子，它变成什么样子以后，能让写Rust 内核模块的人会变得好过一点。就是语言和 OS 可能都得做一些改变以后，才能让这个东西变成一个更加让写 Rust 的 driver 的人更加舒服一点。不然他可能本来他想用 Rust 的便利去写内核模块，结果写的又不像 Rust 的，因为要适应内核的一些基础设施或者编程规范嘛。我的问题不知道周星转没有。
Okay, it's quite long for me to translate. So basically, I think the spirit is that the kernel has accumulated a lot of infrastructures over the years, including RCU and other stuff, and then but then Rust also has its own infrastructures, so there can be some incompatibilities. So you will actually write Rust code that doesn't look like normal Rust code, right? It's your suggestion is to maybe we can have some changes in both Rust side and kernel side to actually kind of compensate for this incompatibility and maybe kind of unify them together. And this is a very valid question, we actually have to come up with different kind of abstractions for the RCU, etc. And you can also see in slides, which I have it previously, where like this is definitely not the economic Rust code that you have, right? But the difference is more in how things can be done in the kernel, but not with the existing infrastructure. Like in kernel, inherently in some context, you couldn't do allocation. That's not related to it being like kernel is already structured in such a way. It's that fundamentally in some context, you shouldn't do allocation at all. Right, so more, I think the difference is more on that front rather than the API and accumulation of infrastructure in the kernel. Is this answer satisfying or? Okay, sure.
我还说中文吧，就是两个小问题。第一个是现在这个 Linux 它有一个 FreeRT， 这个是现在这个 support 这一块。
So the first question is, does this support preempt RT? The answer is yes.
OK， 第二个问题是最后一页说有很多的就是挑战 challenge， 哪些是由于你要跟 Linux 结合引入的，哪些是其实只要写个 Rust kernel 就必须要去考虑的问题。
The second question was, I list a lot of challenges in the Rust for Linux project, and how many of them are related to integrating into the Linux kernel, and how many of them are inherent to writing operating system in Rust. I think it really depends on what kind of ideology of the operating system you are actually working on. So if like you can bear with additional allocations, and like you can maybe structure the API different way. Like for example, in Windows kernel, for example, it does more allocations than the Rust kernel has. But it also has some, in some contexts, you still couldn't do allocations, right? In interrupt handler, for example, you might not be able to do allocations, or in some cases, in Windows kernel, allocation can still fail, which also brings the unique challenge of failable allocation in many cases. So I would say quite a few of them, like majority of them, should be is related to the inherent challenge of writing operating system kernel in Rust. But some of them, for example, the dynamic loading nature of Linux kernel might be not present in a unit kernel or a monolithic kernel where everything is compiled together, right? But it will be a challenge for Windows, for example, where you have different drivers loading all the places. And like the intrusive linked list might not be a challenge for many kernels that does not use this kind of technique. But for allocation, I think this is a universal challenge for all the kernels. Are we having more?
Hi, I have two questions. The first one is that how do you balance the code in Linux, in C, and Rust? What kind of components should be written in Rust, and how do you balance that in the future?
So currently we are not going to restrict arbitrarily on what driver should be written in Rust or what driver should be written in C. So basically, like we are trying to provide abstraction for all the possible subsystems, but it's up to the maintainers of subsystem to decide if they were willing to accept Rust bindings.
Okay, so my next question is that during your presentation, I think it is some kind of Rust APIs change quite different from the traditional, like how we write Rust. Do you have some kind of like guidebook or document to guide people if they want to contribute to write for the Rust?
So
and I think it is kind of hard right now for normal Rust contributor or writer that familiar with the current Rust style to contribute to this project. And also, you have mentioned that there are a team for Rust for Linux. So it made me wonder that, because if I want to contribute to Linux project,
So the one good thing about Rust is that Rust docs really works really well, right? If you go to rustforlinux.com, on the navigation link, you will see the generated Rust docs. So we aim to provide as much as detailed Rust doc as possible, and it's all generated by the Rust doc tool, so it looks all familiar with the rest of Rust ecosystem. And then we are trying really hard to actually document all the like conditions of functions that to be called. Because if you ever do kernel C side of kernel programming, you will see the document is not very thorough. You have to actually dig into the details of implementation to actually understand what the function is doing. And we are trying to change this by leverage Rust doc essentially.